In this video, I want to introduce you to the concept of formal charge and walk you through the method for calculating formal charge. But before we begin, I want to point out to you that formal charge and oxidation state are not the same thing. So in your general chemistry classes, you probably learned, I'm sure you learned about oxidation state and determining oxidation state. Formal charge is a little bit different from oxidation state. Both of these are methods of accounting for electrons, or electron accounting. However, when you determine oxidation state, you may remember that if you had a bond between two atoms, the pair of electrons, or the two electrons that made up that bond, were assigned to the more electronegative atom. Well, when you're calculating formal charge, when you have a bond that's between two atoms, or a pair of electrons shared between the two atoms, you split that pair of electrons between the two atoms when you're assigning them. So each atom from the two atoms that make that bond are assigned one electron from the bond. Just a little bit different method of electron accounting. Now, there's a couple of different ways that you can think about formal charge. But formal charge is equal to the number of valence electrons in the neutral free atom, and this you get just by looking at the periodic table. So you look at which column or which family this atom is in the periodic table, and to get that number. And then you subtract from that all of the electrons that you assign to the atom. What are the assigned electrons? Well, this is going to be equal to the non-bonding electrons, or the lone pairs of electrons, plus half of the shared electrons. So another way that you can think about this is that formal charge is equal to the valence electrons in the neutral free atom minus the number of bonds and the number of unshared electrons. So that is also equal to all of the electrons assigned to the atom. Or you can say it's equal to the valence electrons in the neutral free atom minus half of the bonding electrons plus the unshared electrons. All right, and I think this will be a little bit more clear as we work a few examples. So before we start, let's go through some of the steps. And the first and most important thing is you have to start with the correct Lewis dot structure. So this is why I'm including a few more Lewis dot structures in this video, because you must be proficient at drawing those Lewis dot structures. So you should also note that if we're looking at a neutral molecule, the sum of those formal charges should be 0. Makes sense. If you have an ion, the sum of the formal charges should be equal to the overall charge of the ion. And whenever you have an atom in a Lewis dot structure that has the number of bonds expected on the basis of its group number, it has no formal charge. Or in other words, if it fits one of the bonding patterns that I showed you in the previous video on bonding patterns, then you would have no formal charge on that particular atom. And again, we'll look at a few examples in this video. Checking on these points that I've described above is a good way to check and see if your Lewis dot structure is correct. So if we go back and look at these common bonding patterns, or what I'm calling normal covalent bonding patterns for these second row elements, and we can calculate the formal charge on these second row elements, or on these atoms, because it doesn't matter what they're bonded to, because unlike calculation of oxidation state, we're going to split each bonding pairs of electrons. So if I look at carbon, my group number is 4, or the number of electrons in the neutral free atom is 4, and then I subtract from that 1/2 of the bonding pairs. So I have 4 bonding pairs for 8 electrons. Half of those 8 electrons I assign to carbon, or I can say I subtract the number of bonds from that. That gives me a formal charge of 0. For nitrogen, remember that we have 5 electrons in the valence shell, and the number of electrons that I assign is going to be equal to the number of bonds. We have 3 bonds, plus we have 2 electrons in a lone pair, so we have 5 minus the quantity 3 plus 2, which is equal to 0. For oxygen, 6 electrons in the valence shell, and the number of electrons that I assign to oxygen is equal to the number of bonds plus the non-bonding electrons, or 2 plus 4. 2 bonds plus 4 non-bonding electrons. So I have a formal charge of 0. For the halogens, remember I have 7 electrons in the valence shell, and the number of electrons that I assign in this particular bonding arrangement is going to be 1 for one bond plus 6 for the lone pairs of electrons. The 3 lone pairs is 6 electrons, for an overall 0 formal charge. Let's look at a few examples now. Let's look at the ammonium ion. And remember that we said that we have to have a correct Lewis dot structure. So let's start by drawing our Lewis dot structure. And this is a pretty simple example. First, remember we add up all of our electrons. We have 5 from nitrogen. 4 hydrogens each contribute 1. We have a plus charge. So that tells me I have to subtract 1 electron. That gives me a total of 8 electrons. Now, nitrogen is going to be my central atom, remember, because it has the highest valence, or it can make the most bonds of the 2 types of atoms that we have in this molecule, or in this ion. Hydrogen can never be used to connect 2 atoms because it can only make 1 bond. So you could never use hydrogen to link 2 atoms together. So the only arrangement that I can make has nitrogen as the central atom and 4 hydrogens bonded to that nitrogen. Now I've told you that we have an overall positive charge, and let's figure out where that positive charge is. I also want to point out to you that from here on I'm going to start using a dash or a line to represent a bonding pair of electrons, or to represent a bond, and you'll see that we will start doing that pretty much exclusively when we start working on different types of representation of structure. Just because I don't want to draw all of those dots to represent all of those electrons, it's a lot easier for me just to draw a dash. So let's calculate formal charge for each of these atoms. And on nitrogen, remember we start with 5 electrons in the valence shell. We have 4 bonds. Those 4 bonds comprise 8 electrons, but I only assign half of them, because they're bonding pairs, half of them to the nitrogen, so that becomes 5 minus 4 equal to 1. For my hydrogens, I have 1 electron in the valence shell in the neutral free atom. I have 1 electron that I assign to each hydrogen atom, because each hydrogen atom has only 1 bond. That's 2 electrons, but I only assign half of those electrons to the hydrogen. So overall, if I add up my charges, I have 1 plus 0 for an overall charge of 1. Let's look at the nitrate anion, NO3 minus. Again, we have to have a correct Lewis dot structure, so let's add up our electrons. Nitrogen has 5. I have 3 oxygens, so that's going to be 3 times 6, or 18. I also have a minus charge, so that tells me that I'm going to have to add in 1 more electron. And now I have a total of 24 electrons for the nitrate anion. Now I have to figure out how to arrange the atoms, and then how to add in all of those electrons to satisfy the valence of nitrogen and my 3 oxygens. So I'm going to make nitrogen my central atom. Nitrogen can make more bonds than oxygen. Remember, nitrogen can make 3, oxygen can make 2. So let's make nitrogen the central atom and arrange the oxygens around the nitrogen. And if you do that, you come up with a structure that looks like this. And you've probably seen the nitrate anion before in your general chemistry classes. You already know what it looks like. And if you count up these electrons, you'll see that we have 24 electrons. But let's look at our formal charge calculation. And one thing you should note is we have in this representation 2 different types of oxygen. We have 1 oxygen, that's oxygen number 1, I've labeled it number 1, that has 2 bonds and 2 lone pairs. And then we have 2 oxygens that look alike, Each one of those oxygen number 2s that I've labeled has 1 bond and 3 lone pairs. So you're going to have to do separate calculations for each of those oxygens. So let's work on calculating our formal charge. Nitrogen, we start with 5 in the valence shell minus 4 for our 4 bonds. So nitrogen has a +1 charge. Oxygen number 1, we start with 6 electrons in the valence shell, and we assign 6 for oxygen number 1 because we have 2 lone pairs for 4 plus 2 bonds for 2 more. So that 6 minus 6 is 0. Oxygen number 2, they're both the same, they're identical. Again, we start with 6 electrons in the valence shell, but now we're going to assign 7 electrons to each of those oxygens. So we have 3 lone pairs for 6 electrons plus 1 bond for 1 more, so that 6 minus 7 is equal to -1. I have 2 of those oxygens, and each one of those oxygens has a -1 charge. So overall, I have -2 plus 1 gives me a -1 charge. Nitrogen has the plus charge. My 2 oxygens that I've labeled number 2 each have a -1 charge. So I have a -1 charge overall. You've probably seen, as I mentioned, the nitrate anion in your general chemistry classes before, and you know how to put that together with the 3 oxygens attached to the nitrogen. But I just want to take a minute to point out that sometimes there are a number of different ways that you can arrange those atoms that satisfy the valence for each of the atoms and fit all of the criteria for a Lewis dot structure. And this is one of these examples. If I didn't know to attach all of the oxygens to the central nitrogen, I might have made an arrangement that looks something like this. And if you count up the electrons, you'll see that we do have 24 electrons that we need. And if we were to calculate our formal charge for all of our atoms, we would see that we have 0 for oxygen. We have 0 for nitrogen. We have 0 for this oxygen. And finally, we have a -1 for the last oxygen, or the oxygen on the right. So overall, I have a -1 charge. So there's really nothing wrong with this Lewis dot structure, except for the fact that this is not the structure for the nitrate anion. And you're going to see that as the molecules or the ions that you're looking at become more complicated, there are more and more possibilities for arranging all of those atoms and all of those electrons. And sometimes those different arrangements represent different molecules, and sometimes they don't. And this is one of those cases where this does not represent a different molecule. This does not exist. But if you gave me this structure, if I asked you to draw a Lewis dot structure of the nitrate anion and you gave me this, I'd probably have to give you credit for this because there's nothing wrong with this structure except for the fact that it's not the structure.